Good afternoon. I'm Saritha Kumari, Assistant Professor, Institute of Aeronautical Engineering College, Dundigal, Hyderabad. Uh, uh, Today the topic is under sag and tension. The topic is stringing chart and sag template. So this is mapped to again the course outcome too. So before going into stringing chart and sag template, so previous in my previous lecture we have seen sag calculation for the towers, that means supports with equal height. So continuation of that, the next case is when supports are at unequal levels, when supports are not at equal height. What is a sag? What is a sag expression? So we can see on the right side there are two supports, okay, two supporting towers A and B, okay, capital A and capital B, which are placed on a hill. Let us say it is a sloping area, a hill example. Then here, small l be the span length. So we know that span length means distance between the towers, and they defined small h. Small h, okay. Small h is a difference in levels between the supports. So this is support A, support B. So the difference between them. So from here to here, okay. The tip of the from the tip of two supports. So that is a H difference in levels. Next to x1, small x1 is defined as the distance of support A first to what is that lower level support A. So it is a lower level support. So compared to the other support, right? So x1 is the distance of this lower level support from the midpoint of the conductor. Okay, from the midpoint. What is the midpoint? O. So for the conductor suspended between these two supports, the midpoint, the lowest point, okay, so is not at the middle. It is not at the middle, right? When supports are at unequal height, so it is somewhere between the two supports, okay, depending upon the height of the two supports. So here, because A is at lower level compared to the other one, so the lowest point of this conductor is near to the lower level support A. So x1 be the anyway x1 be the distance of this support from the O, and x2 be the distance of this higher level support from the lowest point. Next, what is a capital T? We know that capital T already defined as tension in the conductor. Okay, now we want to get the sag expression for this case. So we can see the diagram, okay, how the two supports are placed, okay, on a slope area. Then here, first initially consider small w be the per unit length of the conductor. Small w be the length of the per unit weight for per unit length, okay, of conductor. Then sag expression, sag s1 and s2 are written as wx1, okay, first s1 wx1 square by 2t, because in from the previous case we know that, okay, basically y is given by wx square by 2t, right? From the previous case when supports are at equal level, okay, it is that means we have taken a small portion of the conductor, and we have taken a point along that conductor, okay, whose coordinates are small x and small y, okay. X is the horizontal distance, y is the vertical distance of that point. So then on that small portion the two forces are, okay, a weight of the conductor and another one is a tension in the conductor. So based on that, we have this expression initially. Okay. So that is y is equal to wx square by 2t. Now from this expression, if we write what is the y, vertical distance, right? X1 is a horizontal distance of that particular point. Here, if we write that for lower support A, y is what? Sag with respect to the lower level support. So let us say that that is S1. Okay. So uh, here at support A, S1 is equal to W. What is the horizontal distance here? X1. Okay. In place of this expression, X becomes X1. W X1 square by 2t. And um, similarly, S2. What is S2? Sag for the higher level support B. So S2 is given as W X2 square. What is X2? Distance of the higher level support from the midpoint. Okay, horizontal distance. W X2 square by 2t. So that is how sag expressions for S1 and S2 are written. Okay, now here further it is mentioned here. We need to know basically what is a expression, what is x1, what is x2. Okay, so we need to simplify this. Okay, so um, because see that this is not it's not yet over. So this is further simplified like this. Okay, how it is simplified? See that we know that x1 plus x2 is equal to horizontal. Okay, distance total value is equal to length of this span. Okay, that means x1 plus x2 is equal to L. Now subtract these two. Okay, okay, that's what it is done. So S2 minus S1 is equal to W by 2t is common in both. So x2 square minus x1 square, right? S2 minus S1 is equal to W by 2t into x2 square minus x1 square. So now it is further expanded a square minus b square. Okay, a plus b into a minus b. A plus b into a minus b. So that means x2 plus x1 into x2 minus x1. Now we know that sum of x1 plus x1 and x2 is given by L, right? So that's why it is the next step WL by 2t into x2 minus x1. Now from this, how it is further can be simplified because we know that S2 minus S1 difference between the two between difference between the height of the two towers, it is given as defined as in the beginning small h, right? Okay, small h. So that is nothing but s2 minus s1 is equal to h. So it is substituted here. Okay, so h is equal to wl by 2t into x2 minus x1. Now, finally, x2 minus x1 is written as 2th by wl. 2th by wl. So, this is the expression for x2 minus x1. And we know that x2 plus x1, sum of the x1 and x2 is equal to L, right? So, if we simplify these two, okay, we will get the expressions for x1 and x2. If we simplify these two expressions, we will get the expressions for x1 and x2. Okay, so the expressions you can see here, x1 is equal to L by 2 minus TH by WL, and x2 is equal to L by 2 plus TH by WL. So these are the two expressions, okay, for x1 and x2. Expressions for x1 and x2, okay, are given as, okay, so x1 is equal to L by 2 minus TH by WL, and x2 is equal to L by 2 plus TH by WL. So that is how in this when supports with unequal heights, the x1 x2 values are calculated. Suppose we will have problems also based on this sag and tension concept. So later we'll see the problems. So, using given data to calculate sag, okay, when supports with unequal heights, okay, first we have to suppose if they ask you to calculate sag. So, lower level sag is 1, higher level sag is 2, right? So, the expressions involves x1 and x2, right? So, okay, so x1 is calculated like this using given data. Okay, length of the span they will give tension, height, okay, w, weight for the for unit length of conductor, small l, all values are given. Okay, similarly x2 also calculated. So then we can calculate the sag. Okay, so this is the sag calculation. Sag calculation when supports are at unequal heights, unequal levels. Okay, continuation on the same thing, sag calculation. Uh, we need to see the sag expression, how it will change because of the effect of uh, the because of the effect of this weather. Because in the beginning we have seen, okay, that means what are the factors affecting the sag, okay, and tension. So we know that basically sag is affected by not only with the weight of the conductor, with the length between the supports, but it will also weight with respect to the weight of the conductor. Okay, so that means atmospheric conditions. Okay, so temperature conditions, so and so on like that. So basically, the main thing they have studied is how the effect of wind, okay, and also ice loading during stormy weather conditions. Okay, in winter countries, uh, there will be a ice snow falling during winter season, so there will be a ice formation, okay, on the ground. So similarly on the overhead transmission lines which are exposed to the atmosphere. So this is the main parameter. Okay, we need to know how the sag is going to affect, okay, because of this wind and ice loading. So you can see, we can see on the first diagram. The first diagram shows the effect, the ice coating. So if this is a conductor in a circle, okay, if there is a snow falling during winter season, there will be a ice layer around the conductor. So this is what it is shown, the lines, okay, the ice coating. So here that is defined as small t. Small t is the thickness of the um, thickness of the ice coating. Small d is the diameter of the conductor. Okay, now, so here see that the total weight now. The first one shows the because of the ice coating, that is called ice loading. Okay, the conductor weight is increased now, right? The second figure shows wind effect. Okay, so the wind blows horizontally, right? So that's why it is shown like this. Okay, so the wind effect on the conductor. So the total weight of the conductor is given as, okay, included these two effects also, along with the along with its own weight for the conductor. Okay, the wind effect is considered horizontally, that is component shown as W suffix W, and the vertical component of weight is given by its own weight of the conductor, that is W plus ice effect. Okay, so that is a vertical component. So the resultant of these two, okay, vector sum of these two will give the total weight. Okay, so wt is given by square root of w plus wi whole square plus ww whole square. Okay, so vector sum of the vertical component square plus horizontal component square. Now, also look at the one more thing. The defined theta with the angle between the vertical component of the weight and also the resultant component. Okay. Now, how to calculate this weight of the weight with respect to due to ice, and also wi and also ww. First, look at the own weight of the conductor w. So w, we know that weight of the its own weight, conductor own weight. So weight of the conductor per unit length, right? So that is given as, we know that initially conductor weight can be calculated as density is equal to volume mass by volume. So from this, the weight of the conductor is nothing but density, conductor material density multiplied with volume per volume of the conductor. That is what it is mentioned. Okay, so weight is equal to density conductor density multiplied with volume of the conductor per unit length. Next, Wi, weight of the ice. So it is, see that per unit length, again it is calculated. So it is also density of ice multiplied with volume of ice. Okay, density of ice multiplied with volume of ice is nothing but area of the ice coating. Okay, area of the ice coating, calculated, that is multiplied with per unit length, so into 1. Okay, volume of ice calculated as, given as area of ice coating multiplied with 1 per unit length. So how the area of the ice coating is calculated? Okay, pi pi r square, right? Area means, so in, if we write in terms of d, it is, radius means d by 2, right? Pi by 4 d square. What is the d here? Consider the total diameter. Okay, so that is nothing but, look at the first figure left side. Total diameter is d plus 2t. Okay, so this side is thickness, this side thickness t. Okay, so d plus 2t whole square, from that multiplied, subtracted diameter of the conductor. Okay, so simplified, that gives the area of the ice coating. So if we simplify this, we will get it as pi t into d plus t. Okay, that is a after simplifying this one, we will get this one. So this one we have seen, this one we have seen. Then WW, wind force. What is WW? Horizontal component, right? WW, wind force per unit length. So we know that pressure is equal to force by area. So wind force is given by, that is wind pressure multiplied with projected area. Wind pressure multiplied with projected area. So wind pressure, okay, multiplied with how the projected area calculated? Per unit length, right? So what is the total length of the conductor? D plus 2t, right? So that's how, length multiplied with per unit length. So that is how WW calculated. So on the same thing, one more thing, based on this factors included, the sag expression is given as like this. So the sag expression finally given by WT L square by, we know that WL square by 2T, where what is the W? Total weight. Okay, how the WT total weight, how it is calculated previously? Okay, we have seen. Okay, phasor sum of the those three. Now, here this sag is calculated like this, is a slant sag. Okay, it gives a slant sag because total weight, how it appears. Okay, it is like this, right? Total weight. So they called it as slant sag. So makes an angle theta to the vertical. So suppose in the given problem, if they didn't ask any thing about the sag, just calculate this slant sag. But if they ask us to calculate vertical sag, we need to consider that vertical sag means, what is a vertical sag means? This component. So that is given by, this component means, from this figure, S cos theta. Okay. So now how the theta is known? From here. Okay, so it is understandable. Tan theta can be written from this diagram like this. So that is how the effect of wind and ice loading considered. Okay, for the calculation of sag. So next topic, string chart. I will continue in my next lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.